In part 2 of this topic, we're going to be looking at rational functions that have quadratic denominators. Whenever we see an integral that has a quadratic denominator, there are a number of paths before us, so we have to have a few questions that we can ask ourselves. The first of which is, can we factorize? So if we see a quadratic that looks like this, we know that we can factorize this expression into x minus 1 times x plus 2. However, when we factorize a quadratic like this, this will be more of a focus in our next video. What about if we have a quadratic that looks like this? Is that a perfect square? Yes, it is. Hopefully we can recognize perfect squares when we see them. So in this case, we get x minus 2 all squared. And this is something that we will be focusing on in this video. If we don't have a perfect square, then we ask ourselves, can we complete the square so that we introduce a perfect square into our question? Finally, we need to be aware of the standard integrals and ask ourselves, does the question I'm doing, does it match up with any of the standard integrals that I'm familiar with? All right, time to get into some examples, see what we can recognize along the way. Let's go. So in our first example, we have 1 over x squared plus 2x plus 1. So first question, can we factorize? And the answer is yes. And what type do we have? Well, hopefully we can see that this is a perfect square. And we get 1 over x plus 1 all squared. From here, it becomes relatively simple. We can use the chain rule. So writing out our integral with a negative power helps. And yeah, let's apply the chain rule. So we raise the power by 1. And we put it over this power, along with the inner derivative, but that's just 1 in this case. There's our constant of integration. And just tidying things up, we get minus 1 over x plus 1. All of our examples will be indefinite in this video, so we'll keep tagging on that plus c. Okay, so that's the first one, quite straightforward. On to our second example. So quadratic denominator, can we factorize it? No, we can't factorize it. It's not a perfect square. We can't complete the square either. But hopefully we recognize that this is one of our standard integrals. This is the inverse tan integral. There's nothing fancy added to it, so this is simply inverse tan of x plus c. Okay, so very quick one there, but that leads us on to inverse trig integrals that are a little bit harder, not quite as obvious at first, such as this guy. So x squared plus 2x plus 5. That quadratic by itself, we can't factorize. So we need to think complete the square. So how do we complete the square? Well, we take this middle term, so to speak, we halve it, halve the coefficient. So 2 divided by 2 is 1, and then we square that. So 1, if we saw a 1 here, then we would recognize a perfect square. So let's go ahead and split this 5. So we have 1 over x squared plus 2x. We want to see a 1, and so we've split this 5 into 1 and 4. And now if we focus on this part, we now have a perfect square. So we can write it as 1 over x plus 1 all squared. And then we could write plus 4 again, but we notice that that is 2 squared. And so now we have a form that matches up with example 2. A little bit more complicated, but we can now see that this is an inverse tan question. Now, rather than just x squared, we have x plus 1 squared, so that's like our new little function of x, but the derivative, f dash x, is still just 1, so that's good. So we have our inverse tan of x, that's x plus 1, but we don't have 1 anymore. We've got an a squared value, so 2 is our a value. Okay, so we have x plus 1 on 2, but we also have to remember there's a 1 on a out the front, so for us 1/2. Okay, so use your reference sheet there to help you and practice those ones. Alright, example 4. Sometimes our quadratic denominators are underneath a square root, but that's okay because, once again, hopefully we recognize the standard integral form for inverse sine, so another one of our inverse trig integrals. So in this case we have, if we think of it as a squared minus x squared, okay, we can see that this fits in with inverse sine, where a is once again 2. However, we just have x as our function, and so we get inverse sine of x on 2. So another quick one, but we need to recognize that. And then let's do a harder one that will match up with this form. So example 5, we have 1 over the square root, and we've got a quadratic under there, so we should maybe be thinking that inverse sine is where this might lead. But this form of the quadratic is not very nice at all. So we want to get it more into this form. Okay, so what I would recommend is focusing on your quadratic and looking at your negative x squared and making that positive. So 3 minus, and then we'll put the rest in brackets. So we'll bring out that minus 1 as a common factor. So we have x squared plus 2x. And now just off to the side, let's focus just on this section. This 3 minus x squared plus 2x. So here we want to complete the square. Okay, what do we need to do? Well, halve the 2, square it. So we want to introduce a 1. Okay, but we can't just introduce that 1. That would change the whole question. So at the same time, we'll subtract 1. So nothing's really changed, but now we have what we want. We have a perfect square. This minus 1 is inside the brackets though, so let's bring that out. So we'll leave the x squared plus 2x plus 1 in the brackets. We can't just bring out a minus 1 though, can we? Because there's a minus out the front of these brackets. So this is minus 1, so plus 1. And once we do that, hopefully we can see that here's our perfect square, and we also have a 3 plus 1. And so we can now rewrite this as 4 minus x plus 1 all squared. And we have it in the form that we saw in example 4. So we can go ahead and use inverse sine now. So we have inverse sine of x plus 1, that's our little f of x, over a, or over 2 for us, plus our constant. And there we go. Okay, let's keep the examples rolling. Example 6. The integral of 2x plus 1 over x squared plus x plus 1. So far, we've had 1 on the numerator for everything, and now we've got this linear function. So does this make it trickier? Well, no, this one's actually pretty straightforward as well. If we recognize that the derivative of our denominator, the derivative of our quadratic, is 2x plus 1, and that's exactly what we see on the top. So this is another standard integral form. This is our natural log integral. So we get the natural log of the absolute value of the function on the bottom, our quadratic. And remember, if you notice that the derivative of your denominator is really close to the numerator, it's just out by a constant, then we just factor that constant into account. Okay, so that one's nice. But what if we get a question where the quadratic on the bottom and the linear numerator, we think, okay, derivative of the bottom, I've got a linear on the top. You know, this looks like I should be able to use the natural log, no worries. 2x plus 2. Oh, right, the derivative of the denominator is 2x plus 2, and there's no way we can sort of just adjust by some constant. So what do? Well, this is a case where we can still make it look like what we want. So on the top, we would really like to see 2x plus 2. But that's different to what we started with, isn't it? How is it different? Well, it's like we've added another 1, right? We had plus 1, we've now got plus 2, and so to compensate, we need to subtract 1. So we're not compensating by multiplying or dividing by some constant, but rather it's just within here, sort of like what we were doing previously with completing the square. And so what does this allow us to do? Well, it allows us to now split this into 2 fractions, right? One with 2x plus 2 as the numerator, and then a second fraction with 1 as the numerator. And now we can focus on each of these individually. So the first one, right, the reason we created 2x plus 2 was that now we have the natural log of the absolute value of x squared plus 2x plus 3. But what about this second one? Well, there's a little bit of work to do first. Okay, this now becomes like some of our previous examples where we look to factorize this or complete the square in this case. So x squared plus 2x, we've seen that before. So we want to have a plus 1. So x squared plus 2x plus 1. However, that 1 has come from the 3, so there's still 2 there. Okay, and now we can use the perfect square rule for this part. So give ourselves a bit more room. Okay, so we still have this natural log function. Let's write that out. And this part becomes x plus 1 all squared plus 2. Now we know that this has got to be some function of x squared plus some constant a squared. Previously we've had values like 4, so a nice square number, but it doesn't really matter, does it? Because we know that the square root of 2 all squared will give us 2, and so that's our a value. So let's write our final answer. Writing down the natural log first, and then we can focus on this one, which hopefully we recognize as an inverse tan. So we have 1 over a, so 1 on root 2, inverse tan of our function, our little function, our inner function of x, so x plus 1 over a. plus our constant. Okay, so that one had two things to recognize within it. So first of all, we had to split it up to get sort of what we wanted. Then we could apply the natural log integral. So that bit was okay. We saw we had it 3 times repeated. But then the second fraction became an inverse tan integral, but not necessarily one that we would recognize straight away. We had to take this quadratic denominator and complete the square, and once we did that, then we see that it's in the form of inverse tan. So quite a few techniques there. Okay, let's do one more example to finish off this video. And in this final example, we have x squared on the numerator. So we've seen x squared plus 1 on the denominator before. Might make us think of the inverse tan. But what are we going to do with this guy? And it's not, we can see, okay, the derivative 2x, it's not a linear numerator, is it? One thing we might notice is that, okay, they're so similar that in fact if it was just a little bit different, we would get some really nice cancelling. So what would we need to do to make this numerator look exactly like the denominator? Well, we would add 1, wouldn't we? So if we had x squared plus 1, then it would just cancel with the x squared plus 1 on the bottom. But of course that's not what we had originally. So if we've added 1, we also need to subtract 1. And then we can do a similar thing to before, where we take this part and put it in its own fraction. So x squared plus 1 over x squared plus 1. And then we write our second fraction, which is minus 1 over x squared plus 1. Now the first just simplifies to become 1. And then we still have this guy. And now this becomes a lot more manageable, doesn't it? The integral of 1, well, that's just x. And here we actually have just our standard inverse tan answer. And so there we go. Okay, so we had to once again be a little bit creative with our numerator to get something that we wanted. All right, 8 examples. That's probably enough. Well done. Good luck with the exercise questions.